Okay, we are back. All right. Uh, so I'm saying there is a, what was I saying? There is a 3072 dimensional space. Let's assume this is it. I can only draw 3 dimensions, right? But there are 3072 axes like this. If I do that, every one of these images is a point in that space. Okay. Now the hope is, if I have a good feature set, the hope is that the points of one category will be closer to each other in that space from points of another category. Okay. And the classifier essentially is learning to separate them. That's a good set of weights. It's essentially learning to separate them. So the hyperplanes it's drawing are in those 3072 plus 1 dimensional space. So 3073 dimensional space, that's the hyperplanes passing through origin. Or you could say 3072 dimensional space, then hyperplanes are not passing through origin. There's a bias vector there also. Okay, so conceptually, it's trying to say what type of colors can distinguish between, let's say, this row and this row. That's where the hyperplane will pass between those two data sets. Okay. So I'll say all kind of bluish colors are ships, for example, because there's a lot of blue in those images. That's essentially what it's trying to learn. Okay. Now these classes themselves might not be very compact because you see there is a lot of variation in them. Okay. But still, whatever examples you are given, it's trying to separate them out into classifiers. Okay. Here's an interesting visualization. These are the weights that the classifier has learned after some good training. Okay. Now what was the dimensionality of the weight vector? It's 3072 dimensional, which is about as big as the image. So I can, like I rearranged the image into a vector of 3072 dimension, I took the weights that I learned and I kind of made an image back out of them. So this is the image of weights. Okay, I didn't do that. Andrej Karpathy did it. I'm just saying I mean this is how they were generated. Okay, all right. So this gives you kind of an understanding of what the classifier has learned. Notice that for a plane, it has really learned that the weights that correspond to a plane are really like they are blue all over, but there is a little bit of shading and something in the middle. And that's kind of like something that it's kind of like a filter which will give high response to planes because the structure matches to planes. Okay, in those who know signal processing, this is a match filter. Okay, this is a match filtering approach. I mean, we didn't give this approach. That's what the weights were learned by gradient descent. Okay, look at a car. It kind of makes sense, right? That's kind of like an average car if I'm looking from the front. And maybe in my data set, a lot of cars were from the front. On average, there were more cars which are frontal or almost frontal. And so I can see the windshield structure and the bumper and so on, because that's what kind of the classifier has learned as weights. This, when multiplied by the image, if the image was exactly like this, it would give you a high response. Okay. A bird, it turned out that in our data set, a lot of birds were such that the background was green. And so that's what it has learned. Birds are like green background with something brownish or something like this in the front, and there's a shading thing here. Maybe you can even make out a tail here, because that's how the average bird was. Okay, and a cat, you can see the pointy ears. Okay, even the cats were in a lot of poses, so there is a lot of blur here, but you can kind of make out the cat. And this is what a deer looks like to our network, a linear network. This is what a deer looked like, and a dog, and a frog, and a horse. It's interesting that horses seem to have like two heads here, right? There's a head here and there's a head here, because a lot of images in our data set were side views of horses, and some of them were pointed this way, some of them were pointed that way. So the linear classifier learned like both of them in some sense. Okay, and a ship and a truck. Now let's get back to your question. Why did I do this in grayscale? Well, let me make this rather rather controversial comment here. This classifier has not learned much, right? To the classifier, a plane and a ship are awfully close to each other, except a ship has some white in it, surrounded by blue, and a plane might not have that white in it, surrounded by blue. And in fact, if I was in grayscale, the plane, the ship, the bird, the deer, and maybe even the frog were all going to be similar in grayscale. In fact, the classifier has not really learned what is a deer. It has really learned that a deer is like a brown blob on a green background. That's what a deer is. So, I mean, we are a bit lucky that the classifier didn't contain, let's say, another category which was goats or something like that, some other animal in a similar environment, because then this particular strategy would not have been able to distinguish between them.
So in case of plane or bird, this filter will give the highest ones if our image is centered, if the object is centered.
Yes, yes.
That's because our data set was.
That's how the data set was, and so you can.
The data set is like the object is separated in whole image.
I will still try to distinguish it. The one set of weights. I remember it's a linear classifier, so there is only one set of weights for each category. So that one set of weights that best distinguishes this from the other classes. Okay, I'm trying to build a picture in your mind of what those weights are looking like. The weights will try to replicate your data set. So if the data set has certain biases, I learned those biases, like ships always being on a blue background. I learned that. Okay. Now, if you give me an image of a ship, which is, let's say, looking in a dockyard, for example, the ship is inside some sort of hangar structure or something, it will not recognize it as a ship at all, because that wasn't represented in the data set, so it didn't learn it. In fact, there is a very interesting recent paper just a few weeks ago that I happened to skim, which argued for deep learning, what does the classifier learn? And they said in a lot of problems, the classifier is learning the context in which the object is embedded rather than the characteristics of the object themselves. Because the context has more pixels in the image, and so that's like easier to learn for the classifier. And the way they showed that was that they took a data set which was well classified by a deep learning network, and then they took those images and photoshopped them to just change their background characteristics into some other random background, and then they gave them back to the classifier, and the classifier had no idea what these images were. Okay, so there's a criticism of what the classifier is learning and whether that's even making sense or not, even for more complicated classifier than this very simple one. Yes. No, they give the whole image to learn. It turns out that a lot of images are, a lot of objects have some specific context to them anyways, and so learning that context might not be, learning that background might not be such a bad idea at all. Like ships typically are in the sea, so learning that the blue color here around it is giving support to my hypothesis that this is a ship is not such a bad idea. But I'm saying what this paper showed is that when you do this strategy, there is an overemphasis on the context, and then if you change that context, you can get very random classifications, even for something very sophisticated, a very sophisticated classifier like the one which is used in Google goggles. We'll look at that structure of how they do it. Yeah. It depends on the learning process, and we'll see the dominant practice in learning process in just a moment of how we do that. Okay, but this is just a linear classifier. Hypothetically speaking, what is the linear classifier doing? Like I said, there is a high dimensional space, and in that space we are separating out our class. We are separating out the region of our class. Each one of these, I show this as a line. Well, this is really a hyperplane, but actually the function has values all over. It's just that on that hyperplane the values are 0, and otherwise on one side it's positive and on the other side it's negative. And so it's trying to give your class the highest value. Each one of those weight vectors is going to give that class the highest value and everybody else 0, so that when I put them together, that class gets the highest value if the correct image is given to it. All right, done? Any questions? Okay, so Yeah, well, one last question here. What would be a hard set of classes to learn for the linear classifier?
इसमें बेसिकली डब्ल्यू का स्ट्रक्चर कैसा होगा? अगर 10 नोड है तो वो लीनियरली इंडिपेंडेंट होना चाहिए क्योंकि अगर दो सेम आ रहे हैं तो उनका तो डिपेंडेंसी होगी। इन टर्म्स ऑफ मैथमेटिक्स डब्ल्यू की कंडीशन होनी चाहिए कि फर्स्ट एंड सेकंड लास्ट जो है इसमें कोरिलेशन काफी ज्यादा है, सो इन ये दो रोज काफी डिपेंडेंट होंगे, सो अंडर डिटरमिनेट सिस्टम
W is a linear mapping. So that's a good question. W is a linear mapping from these many dimensions, 3000 to 10. Okay, so it's like a change of bases. You can think of it as what PCA would have done, except I have put no condition that these bases should be orthogonal. I have that condition on PCA. I've put no condition there. Whatever these bases are, these are linear so far because I have a linear classifier. So these are linear, but I've put no condition on them. What should be their magnitude, what should be their relative angle, and so on. I've put no condition on those. They are being learned through the learning process. There is no independence condition here or orthogonality condition here. Okay. Yes. Any other question? All right. So my question here. What would be a hard set of classes to learn for the linear classifier? Yes, they look similar. They are not as distinct from each other. Theoretically speaking, in that space, if there is a class which is spread around and there is another class in between it, right? Let's say there was in 2 dimensions, there was a donut type of structure for classes. One class sits in the middle, there is another class spread around it. The linear classifier is not going to be able to do a good job. All right. Okay, so we will end this module. We are done with our basic understanding of machine learning, where we looked at supervised learning, unsupervised learning, and in supervised learning, we concentrated on linear discriminant functions. Okay, and with that knowledge, here we go. And with that knowledge, we are going to start talking about the last module of the course, which is deep learning, the new paradigm in machine learning, which is causing a lot of buzz. Okay, and now I will start with this by just talking about linear classifiers as I did in the previous module, and you know what is a linear classifier and you know how to train for it. You can do a gradient descent procedure by setting up some cost function, some reasonable cost function, and doing a gradient descent procedure. Okay, so this is a picture we have seen before. Okay, I just drew it now this way, I drawn it the other way, but this is a picture we have seen before. It's basically what is the function that you would get here. You will get x0 times a0 plus x1 times a1 plus x2 times a2 dot xd times ad. Summed all of that up, you get a value, and then you threshold for a 2-category problem. Okay, and then the question is, how do you find these weights A? So you can actually find them by this procedure, which is the gradient descent procedure. And if you don't like this, you can use stochastic gradient descent if your data set is very large. Okay, so this is a linear kind of machine. It's a linear two categories. It's a 2-category system, which is doing a linear combination of your input values, data point, with the weights. Okay, so that's really if I call this x0 to xd, I call that y. Then really what I'm getting is A transpose y, and then I pass this A transpose y in a threshold function here. Okay, just to map it. If I get a positive value, I'll map it to +1. I get a negative value, I'll map it to now -1. So that becomes a decision. I get a discrete classifier out. Okay, so we are familiar with this picture. There is just a new name here. This is actually called perceptron. In fact, there is a very slight change between a perceptron and this, but that's actually insignificant, so we'll just call it a perceptron. Okay, so a perceptron is just a linear discriminant, a linear machine like this. Okay, and what do I have here? This is I'll try to write it a bit more formally now rather than before. This is a unit step function. What is a unit step function? A unit step function is a function like this where this is 0. Okay, so I really took a unit step function and I multiplied it by 2 so that it becomes twice as high. This is 1 in a unit step function. This is the 0 point. Okay, so the y-axis is here, and so I multiplied it by 2. It becomes twice high. Then I subtracted 1, so it becomes this function. Okay, so that's kind of like a function which is applied at the end on whatever value that dot product is given me. It's applied at the end to kind of get a decision. All right, so is this picture perfectly clear? We have kind of seen this before when we talked about linear discriminant functions. We saw this before, and I'm going to start from here to motivate neural networks. Okay, all right, so what does the perceptron or this type of linear machine really do? So yeah, I switched notation. I make this W. Previously it was A. I apologize for that. You can just use. Okay, so essentially it implements a linear function of the input. In this case, the input has two values, x1 and y1, x1 and x2. So it's a function of x1 and x2. Okay, it implements a function, and then I threshold. So let's say, just to give you a concrete example, so you have a full picture in your mind. Let's say these weights were this. This was my weight vector. Okay, these came after some training, whatever. So what is going on then? I can actually take all possible values of x1, x2 and plot the function that I get for these weights. Okay, you understand what I did here? I said x1 can vary from minus 1.5 to 1.5, let's say. And I said y1 can vary from, x2 can vary from minus 1.5 to y.5. So I took, in MATLAB, I just generated all those values of x1, x2. You know how to do that mesh grid function. Okay, so I generated all those possible x1, x2 values because it's a two-dimensional space. So I generated all the coordinate values of that two-dimensional space. And for each one of them, I multiplied them by these weights, the 1, x1, x2 dot product with these weights. These are some random weights. I took them. And so these are the values that I got. I have some low values, some high values. They change smoothly all over the space. Okay, and in fact they go from negative to positive because there is somewhere along that the 0 point which will be a line. Okay, everyone understands this picture, right? Yeah.
So why did you be
No, that's how a line function is, right? Oh no, so sorry. Okay, good point. The threshold has not been applied yet. This is pre-threshold. After that, I'm going to apply a threshold to this to make a decision out of this. But before the threshold, it's a linear function. So I plug in some value. If I was exactly on that line, I will get 0. I'll get some positive number. The further away I am from the line, I'll get a higher positive number or a higher negative number. I mean, a lower number in the absolute sense, a higher negative number. So as I go far away from the line, this value changes. And all this change is going to be linear. And so it's like a plane that gets drawn, which cuts the 0 plane at a line. All right. Okay. So if I do apply the threshold, like you said, then I'm just going to get +1 and -1, and this is what I get. This is the point where I'm changing from a negative number to a positive number. Agreed? Is this absolutely clear? You can write code for this yourself. Yeah, no problem with that. Okay. So this is what a perceptron is really doing. Okay, given some W, this is what a perceptron is really doing. Let me learn some useful function from a perceptron. Okay, so I'm going to learn the OR function. What is the OR function? This is what OR function is. I didn't use 0 and 1 as you typically write an OR function. A 0 and a 0 and a 0 is a 0. A 0 and a 1 is a 1 in OR. Instead of 0 and 1, I use -1 and 1. And that's not accidental. I mean, zeros are like weird numbers. You multiply with a 0, whatever, it becomes a 0, right? So zeros are, they kind of like collapse information for you. You don't know what the original number was if, you have no idea what the original number was if you multiply it with a 0, because the 0 is like a veto in the General Assembly, right? It doesn't care what the other side was. Okay, so so what I did was, I mean, this is an OR function, except I just mapped all zeros to -1s. Okay, and I'm going to take that strategy just so that my data carries some weight and my weights also carry some weight. Okay, So a -1 and a -1 is a -1 in an OR function. A -1 and a 1 is 1. 1 and a -1 is 1, and a 1 and a -1 and a 1 is a 1. Okay, that's what an OR function looks like. Agreed? All right. So consider this as labeled data. Your data points are two-dimensional. You have 4 data points here, and the OR function is labeled. So I say, give me a set of weights on the perceptron here such that I can learn this data. You understand the problem? Okay. So this is what my data looks like. This is the -1 point, and then these are the one. These are where any one of them is positive. Okay, so that's what an OR is. All right, and you see it's a linearly separable problem. Yes, I should find some weights that draw a boundary like this. So let me choose these weights. Let's say my gradient descent procedure gave me these weights. Let me choose these weights. So what will happen? Where will the boundary be? Well, that means the function that I'm implementing is 1 times 1 plus x1 times 1 plus x2 times 1. So which means the separating hyperplane will have this equation, right? So if this is the equation of the separating hyperplane, I can plot it. And so it actually comes out to be this, right? The slope is -1 and the intercept is also -1. I can write it as x2 is equal to -1 x1 -1. So that's the line that I get, okay? Which means this is a good set of weights because it is actually separating very well between those two classes. Okay, if I were to plot it like I was doing that other plot, these are my positive points and this is my negative point, and actually when I threshold it, I get this for this, right? So far so good. It's a linear machine and it has learned a function for these weights. These weights are kind of good. All right, let me do one more thing. I'm going to learn the AND function. The AND function is this. Now it will only be 1 if both of them are 1, otherwise it will be -1. Okay, so this is what the AND function looks like. The hyperplane should be here. Now let me choose these weights. These are going to come from learning, but I'm just skipping that. So let me choose these weights, which means this is the equation which is being implemented. If I plot this, it's this. Okay, and then if I show it as a full space, this is what I get. Agreed? So -1 1 1 on this machine will implement AND, and 1 1 1 on this machine will implement OR. All right, these are both linearly separable problems. I want to take the jump now to non-separable problems. Okay, so let me choose some data which is non-separable. One of the data sets which is non-separable is exclusive OR, non-linearly separable. Why? Because, well, this is what an exclusive OR looks like. There is a, in the original exclusive OR, there is a 0 here, 1 1 and 0. Okay, now if I plot it, this is what it looks like. Now this is a problem where no matter what hyperplane I try, I can't separate them perfectly. There exists no line that can separate this data set perfectly. Okay, in fact, this exact example became a curse for neural networks historically, because people came up with the neural networks in 60s, and then in the 70s somebody wrote a very influential paper and he said these are not very good models to learn data because they can't even separate out a simple data set like exclusive OR, because at that time neural networks were only perceptrons, they were only linear. Okay, and so for about 10 years afterwards people gave up on neural networks. Then one guy came and he said, no, we can do that if we do this. And then neural networks became popular in the 80s. And then by the end of 80s, people again gave up on that. And SVMs became really popular in mid-90s onwards. And then 2012, again, neural networks became popular. So they have a very curious history of how they gained their popularity and so on. All right. So the question that I'm posing is that there is no really set of weights that can separate these classes. So this machine that I have, this structure that I have is not good enough for this problem because the problem is non-linearly separable. Okay. Now, I'm going to argue that with a little bit of modification, we can make it very useful. Okay. And let me argue why. I'm going to just derive that. We know from our previous knowledge, that XOR can actually be written as a combination of ANDs and ORs. Okay, let me convince you of that even if you didn't have any previous knowledge. So these are my inputs, all possible inputs that I can get. Okay, so an AND is this function. We have already seen it. Is that correct? There is an error here, right? Oh no, wait. Yeah, this is not an AND of x1 and x2. This is an AND of x1 and not x2. This symbol stands for not. Okay, so not x2 will make this a 1, so 1 and then 1 is a 1. Okay, and all the others are minus 1. So that's AND of x1 and not x2. Now I can also do AND of not x1 and x2. In that case, this is a 1 because this becomes a 1, so 1 and a 1 is a 1, and all the others are minus 1. Okay, so that's AND of not x1 and x2. Now I can OR these two columns together. If I do that, what will be the OR of this? Minus 1 and minus 1, that's going to be a minus 1. And minus 1 and 1, that's going to be 1. 1 and minus 1, that's going to be 1. But minus 1 and minus 1, that's going to be again minus 1. And so this is nothing but an exclusive OR. So what does this tell me? This is a very interesting thing. Well, you knew about exclusive OR before. But the interesting thing about machines here is that, I mean, these classifiers here is that I can make, by a combination of linear machines, I can make a nonlinear machine. Okay, let me try to do that. So I have my OR machine. I know that 1 1 1 here makes an OR machine, and AND machine minus 1 1 1 here makes an AND machine. Okay, so what I'm going to do is I'm going to just implement them like this. Let me see how I can implement them. Okay, so I will take my original x1 and x2, and first I will do not x1, not x2 and with x1. Okay, so that's an AND happening. An AND was supposed to be minus 1 1 1, but I want not x2, AND of x1 and not x2, so I put a minus 1 here. So that first x2 becomes minus 1, and then I'm doing the AND. Okay, so this is AND of not x2 and x1, and then I'm going to do another. So this is really AND of not x2 and x1 and not x2. And now I'm going to do another AND where I put the minus 1 here on the second link. So this is an AND of not x1 and x2. Okay, now what do I need to do? I need to OR them together. So I'm going to put another 1 here because the OR machine needed a 1 here. So I'm going to put another node here, 1, and then I'm just going to put 1 1 1 weights on this. So the function that I will get here at the input of this, before this threshold happens, the function that I will get here will be OR of h1 and h2, but h1 and h2 are nothing but these things, and so I have an exclusive OR of x1 and x2 here, and then I can threshold it and it will be correctly classified. So I put multiple linear machines together, 3 to be precise in this case. I put multiple linear machines together, but I cascaded them one after the other. And provenly, I get a nonlinear machine. A problem which was not separable linearly is now separable by a combination of linear machines. Okay? So just one second. So just to visualize this, so this is my exclusive OR machine, which is a combination of these machines in a specific order, which I derived here. So this is what it gives me. Okay, I get -1 for this region and I get +1 for this region, which is what an exclusive OR is. Remember, this is not a linear boundary. It's the same idea as on a single thing, 2 thresholds, right? So there are like 2 boundaries here. So the lesson here is that by combining 2 perceptrons, well, actually 3, I shouldn't have written 2, but by combining more than 1 perceptron, I can create a nonlinear decision boundary. Yes. Yeah. Yeah. It's not linear anymore. It's non-linear anymore. It's non-linear. I said I combined more than 1 linear machine together, but their combination is definitely not linear because there was no linear machine that could have separated them. Okay. How is it non-linear? You can do the calculation if you want to. You can start computing the function. So what do you have here? You have you have a linear function here, which is 1 and minus x1 minus x1 plus x2, right? And you have another linear function here, which is 1 plus x1 minus x2, okay? But now here you have a combination of those functions. So you can write an expression for this whole function, and you'll start getting x squared terms in it. And that's the nonlinearity which has been created. Some x1 will multiply with another x1.
In terms of feature function, if feature function is 1, x and x2.
No, but I cascaded one linear function and one after it. So I'm now getting x squared. I'll get x1 times x1 somewhere. I'll get x1 times x2 somewhere. So I'll get x squared, and that's what this is showing you. Okay. Yeah, I didn't plot the whole surface here, but if I before the threshold, but if I plotted it, it's going to look something like this in this case.
In the nonlinear, the same boundary be interpreted as more than one hyperplanes.
You could. You could think of it as a combination of hyperplanes. Yes, that's true, because each section of this was linear. Okay, so you could think of it as some piecewise linear boundary, which is nonlinear. Okay, so this is what a neural network is. I mean, I motivated a neural network that I did a particular motivation of a neural network, and then we'll kind of relax it later. But this particular network was just a combination of linear networks combined in a particular order. Okay, I can call this a neural network. In fact, historically speaking, I'm telling you that in the 70s, somebody came up with a paper saying neural networks are not good because they can't even solve an exclusive OR problem. And then the guy who came after that and rescued neural networks research really did a set of very influential papers in the beginning of 80s, who said that yes, you are right, we can't solve any more than a linear problem with a perceptron, but if you put them together, make a larger machine out of them, you can actually solve very complicated problems with this. And he gave exactly this example in his book. Okay. All right. This particular category of neural network here is called a feed-forward network because there are no loops allowed. There is no link that can get you back. Even though there are neural networks like that also, very popular now. They're called RNNs, and there are some other ones also. There are lots of architectures now of different types of neural networks. We'll inshallah look at that. Okay. Now it turns out that this is a very, very powerful model. Why? Because let's say you had data set which was nowhere near linear separability. This data is such that there is a circular class in the middle and the other class completely surrounds it, right? So this is like a donut data set. This is as far back, this is as far away from linear separability as you could have thought of in these two dimensions for two classes. Okay. But what happens is that if you allow a cascade of 8 perceptrons, so you can, like you said, you can interpret it as 8 linear boundaries. So notice the actual class was in blue. That's what you wanted to learn. And what you have learned now differs from that blue class only by these small green triangles. Okay. So putting 8 linear machines together gets you actually very close to the ideal class. The error is very small here now. And putting 16 of them together, you can't even make out those green triangles here because we are kind of very, very close to that. Okay. So this idea that you have a very simple linear classifier, very simple restricted sort of idea, but if you put them, if you put a lot of them together, you can actually do very powerful things for very complicated non-linearly separable data sets. Yes.
So by cascading 8 perceptrons, you mean that we are performing an AND operation on them?
No, there's a perceptron, the output of which goes to another perceptron, the output of which goes to another perceptron. So I'll show you how it is. Okay, but I'm just giving you the idea that if one perceptron layer can draw a linear boundary, then 2 layers can draw 2 boundaries, like I showed you previously, and so 8 layers can draw 8 boundaries. Okay, 8 linear boundaries. Okay. So A feed-forward neural network is something, I mean, I motivated it from the XOR example and from perceptrons, but in general, this is what it looks like. You have an input vector X, which is augmented by 1, just so that the hyperplane passes through 0. So that's your input vector, okay? And then you have a bunch of layers. Let's say I have L layers, cap L layers. Each layer can have its own set of number of neurons in it, number of nodes in it, okay? So I have a bunch of these, we call these hidden layers because they are like in the middle. And how large is L will really be how deep your network is. That's what deep learning is about. In deep learning, we use much larger values of L than what we used to do before the deep learning was invented, okay? And then you have weights on each one of these that you're going to learn. And then in the end, you have some output. If it's a 2-category problem, you can just have 1 output or 2 outputs. And then based on what value you get, you can take a decision. So there is an output layer, L is equal to cap L. And this is what a feed-forward neural networks looks like. Okay. The choice of architecture here, how many neurons to put and how to connect them itself is a hyperparameter, is a bunch of hyperparameters for the network, because that choice is going to change things. Yes.
So the decision will be better than his probability of the class.
Okay, yeah. So what is the decision? If I had a 2-category problem, I can just have 1 output, and then the decision would be whether that number became positive or negative. If it's positive, I'll say class 1. If it's negative, it's class 2. That's the 2-category case. If you are doing the linear machine case, what you'll have is you'll have as many outputs as your number of classes. So you'll get vector values out. I mean, you'll get a whole vector out. So if there were 10 categories, you'll have 10 neurons here in the last layer. Each one will output a value, and you'll see which one is maximum, and that would be your decision.
We need to set a threshold for that.
Yeah, we'll see how we do that. Yeah. I mean, just the max operation so far, but we'll see how we do that. Yeah. Actually, if you think about it as perceptrons, then each one of these which joins here is 1 perceptron. So there's like 1, 2, and 3 perceptrons here, okay? And then there are like 1 and 2 perceptrons here. So the number of perceptrons is actually larger than L because there are multiple nodes in each layer, okay? So, but the nonlinearity is created. Each layer gives me a linear decision. It can give me a linear decision. So I'm actually combining linear decisions together. That's like the mental picture that you can build for this. Okay. All right. So here in between, we have some function also. Like I said, there is a threshold function in the middle. We generally don't use an exact threshold function, but there is some function here that is implemented here. So you get this linear sum from there, and you have some function here that is applied to that. Like in the single case, we were applying the threshold function. You have some function here which is applied, and then it moves forward. And those are called activation functions, and I kind of want to talk about that. So here are some nonlinear activation functions that you can choose. So one of them we already know. That's what we were doing in the perceptron for the 2-categories. But I can choose some other nonlinear function also. Okay. So let me talk about the importance of these activation functions in just one argument. First, you understand what the activation function does. It receives whatever input is, it sums that up, right? But then it passes that through some function. So this is the input, this is the output of that function. And then that value will pass forward. Okay. Everyone clear on that? Okay. All right. So it turns out that a nonlinear activation function is kind of like a requirement for a neural network to do nonlinear decision boundaries. If we don't use it, we run into problems. Okay. There are some activation functions, like I gave you one example, 2 unit step minus 1. That was this function. But tan hyperbolic is also used, and there are a bunch of others. What is tan hyperbolic? A tan hyperbolic is like this blue curve. Okay. So in a sense, and this red curve is that unit step 1. So in a sense, tan hyperbolic is like a soft step function. It's not, it doesn't have hard corners, it doesn't jump immediately, it's kind of like changes smoothly. Okay, and then there are others that people use. We'll talk about those later. Okay, but you can think of some function that I need here. Okay, so here's an example. What does the what does this kind of activation function do for you? So remember, I had this network as AND, and I had a threshold here. Instead of that threshold, I'm going to change, instead of that unit step, I'm going to put tan hyperbolic here. Okay, so what do I get? My surface, if I look at it from the side, it was a plane first, but now it becomes like this. And I will threshold that surface. So if I threshold, so this is what it looks like in color. Notice it kind of, there's more of pink here, and then it changes smoothly to yellow. So there's like a drop, I mean, like an increase. Okay, the step has become smooth. When I threshold this, if in the end to get a decision, I'll still get the same linear decision boundary. But the function has changed here a bit. The underlying function has changed here. Okay, all right. Why do we need these activation functions? So let me give you an example of computation where I don't use activation functions, and then I'll show you when I use activation functions what will happen. And this is actually a very crucial point here that I want to make, a very critical point in understanding neural networks. Okay, so I didn't want to use an activation function. So really I said the activation function is a line at 45 degrees. That just means whatever is the input, pass it as output. Just don't do anything with it. Okay, so that's like a identity activation function. Okay, an activation function that doesn't do any activation, doesn't do anything. Okay, now let me do the whole computation of this network for you. It's instructive anyways of how a network can be theoretically computed. Okay, so I have an input here, x is 3 by 1. Agreed? It's a vector 3 by 1. What do I have here? I have weights here. I'm going to say these are weights of layer 1. So layer number I'm going to put in superscript as parenthesis. So you know, so this is a weight vector of W1. Okay, what's the dimension of this? It's a 3 by 4 matrix if I use as a transpose. So really the layer 1 output would be x1 at layer 1 will be W1 transpose x. Okay, so W really is, so why is it 3 by 4? Because there were 3 things here and 4 things here. Okay, so if I I want to map a 4 vector to a 3 vector really with these weights. So what W transpose should be 4 by 3. Because a 4 vector gets maps to a 3 vector, so which means W is 3 by 4. Okay, so it's some 3 by 4 matrix. Which one you will learn through your gradient descent algorithm, we'll see how we do that, but it's some 3 by 4 matrix. Okay, notice what is this? This is again like a change of basis. You are mapping a 4 vector to a 3 space. Okay, in fact this particular example looks exactly like a camera, because the camera maps a 4 vector to a 3 space. Okay, so it's but that's just because I chose 4 and 3 here. That doesn't have any significance. It's just a linear mapping from one space to another. Okay, now so x1 is a 4 by 1 vector because there are 4 neurons here. Then I have some W2 here. What would be the dimensionality of W2? W2 transpose will be 3 by 4. W2 will be 4 by 3 because I'm using the transpose convention here now. So this is 4 by 3, and so layer 2 output will be x2 will be W2 times x1. x1 is the input now and x2 is the output. So it will be this, and so x2 is a 3 by 1 vector, right? Because W2 transpose is 3 by 4 multiplied by 4 by 1, so that's a 3 by 1. Agreed? And then what is the dimensionality of W3 here? What? 3 by 1. So this will be a 3 by 1 vector, and the layer 3 output, the final output that I need will be x3, which will be this 1 by 3 multiplied by a 3 by 1. So x3 is going to be 1 by 1, which is what I need here because it's the last one. Agreed? Is this absolutely clear? Okay, and I didn't use any activation functions in the middle to complicate stuff, so I just did the simple linear mapping. Each one of this you can think of as a change of basis if you want to. I'm mapping a vector to another vector. All right, now the interesting thing is that what is x3, my final output? Well, it is W3 times x2. But I know what is x2. x2 is W2 transpose x1. So I can substitute that in here. So x3 is going to be W3 times W3 transpose times x2, but x2 is W2 transpose x1. Okay, but I know what is x1 now. X1 is W1 transpose x, so I can substitute that. So x3 is nothing but W3 transpose W2 transpose W1 transpose x. X was the input. Okay, which is what? This is matrix multiplication. Matrix multiplication is associative, and so I can just call it W transpose x, where W is a 3 by 1 matrix. Why? Because W1 transpose is W1 transpose is 4 by 3. W2 transpose is 3 by 4. So that's those two combined are 3 by 3. And then W3 transpose is 1 by 3. So 1 by 3 into a 3 by 3 is a 1 by 3, which means W really is 3 by 1. So what did Shakespeare say about this? Much ado about nothing. That's a Shakespeare play, right? I mean, why did I make such a large network? I really didn't need it. All I needed is 3 weights. In fact, what this large network is implementing is nothing but a perceptron, right? And now it doesn't matter how deep you make this network. If you have one output in the end and you have 3 layer input in the beginning, ultimately, no matter how deep, big, long, fat network you put in the middle, ultimately it's going to reduce to a 1 by 3 vector, because it's a 3 to 1 mapping. And so there is no advantage of neural networks. I mean, I could have just lived with a perceptron. Yes.
Does this prove that all linear transformations can be represented by a perceptron?
Yes. A perceptron is the general linear transformation machine, right? Because a linear transform is A transpose Y, and I can implement that in one layer. So it doesn't really help me at all to make networks deep. So what's the catch here? Yeah. So the catch is the activation function. In reality, this is not what we do. If we were doing this, well, there would be no need. I mean, you give me a deep network and I'll give you a single layer network, a thin network, right? A kamzor, lagar kisam ka network, and it will do exactly the same thing. The difference is the activation function. This is not what is going on. There is a theta s in the middle. Okay. So you have, what is the layer 1 output here? The layer 1 output is not just W1 transpose X, but it's W1 transpose X passed to a theta. So it's theta of W1 transpose X. Right? The notation I'm using is f of x, right? So x passes as input and f of x gives you a value. So theta will give you some value of W1 transpose x. Okay, yani W1 transpose x is passed on to theta. And then what is x2? What is the layer 2 output? It's theta of W2 transpose x1. And what's layer 3? It's theta of W3 transpose x2. Okay. So if I put all of that together, well, x3 is theta of W3 transpose x2, but I can substitute x2, which is theta of W2 transpose x1, which I can substitute x1, so it's theta of W1 transpose x. And so this is not equal to one matrix now, because there is a non-linear function theta in the middle at every stage. So this tiny non-linear function, tiny non-linear activation function, which actually initially wasn't even proposed for this purpose in the original neural networks. It was just proposed as some sort of regularization function in the middle so that the output doesn't exceed a very large number or doesn't become very small. But it turns out that that's actually a crucial component of the neural network. It's not, the neural network is not going to do anything interesting unless you have some sort of nonlinear activation function in somewhere. In fact, it doesn't even have to be the same activation function all over. It can actually be different at different layers. I mean, even that is okay. as long as there is some nonlinear activation function available to create nonlinear boundaries. Only then can we learn difficult problems which are nonlinearly separable. Okay, here's an example. I'm giving you actual numbers now. Here I have 3 and 3, so W should be a 3 by 3 matrix for this layer, W1. So I picked these numbers just randomly. Okay, so these are W's. Here I needed a W which is 3 by 1. Okay, because I'm mapping from 3 to 1, so that's my W2. Let's see what the decision surface looks like. This is what it looks like. It's not like terribly nonlinear. I mean, it's not like very bigly, but that's because I have a small network. But surely it's not a linear boundary now. Okay. In fact, I can show you a bigger network, something more interesting. So here, what should be the size of W? 3 by 1, 2, 3, 4, 5. So I need a 3 by 5 W. That's this one. The first one is 3 by 5. The second one is a 5 by 4. So that's this one. No, 1, 2, 3, 4, 5. Yeah. So 1, 2, 3, 4, 5. Yeah, 5 by 4. So that's this one. And then the last one is 4 by 1. So I'm mapping to a 1. If I do that same sort of code that I wrote to visualize the feature space, this is what I get. Now this is highly nonlinear. Notice how complicated a nonlinear function can be learned with a relatively small network. It's not like a really terribly deep network. It's only like 5 neurons in the first layer and 4 neurons in the second layer. By the way, when we say neurons, don't think about brain neurons. People sometimes take a deep learning class and then they say, I know how the brain functions. Well, you don't, right? The brain is much more complicated than that. So don't think that there is some relationship between the neurons that we talk about and the actual neurons that are in your brain. Those are much more complicated. You're going to look like not a very intelligent person if you go to a neuroscientist and say, oh yeah, neuron, yeah, I have a model for that. No, no, you don't. Okay. The reason we say neurons is because this is kind of like, at best, you can say it's loosely motivated by the human brain, the neurons in the human brain. But don't try to sound like an expert on neurophysiology or something like that. Okay, you're not. I'm not, right? So I don't want you to make that claim. We just motivated it from very simple mathematics. We are trying to learn a function. Okay, yeah. Yeah, I did. I mean, in generating this figure, I generated a threshold. But understand that there's some kind of smooth surface that is learned here. I'm just showing you a threshold of that on zero plane. Yeah. Yeah, in two-class problem, ultimately, in the end, we apply that threshold, yes. Okay. So yeah. So the next point is, how do we determine the weights? There's the famous backpropagation algorithm that I want to mathematically derive just from scratch, not just state what's the backpropagation algorithm. We'll talk about that next time. And the treatment I'm using for backpropagation is from the lectures of Yasser Abu Mustafa at Caltech, which are just like an amazing set of lectures on machine learning. If somebody wants to follow a rigorous course of basic machine learning, not deep learning, just basic machine learning, I would highly recommend. I think there are just about 18 lectures or so of 1.25 hours each, because Caltech is on quarter system, so the total number of lectures are less than in a semester. But those lectures are really very well delivered. He's an award-winning teacher there, professor there, and those are very, very good. And so the kind of treatment of backpropagation that he gave was very well described. So I adapted my slides from those, and we'll cover that inshallah tomorrow. Okay. Any questions? Yes? No? Done. Ji. Oh, so we have a trip today. Those who have signed up for it, right? I have a list of those names, those who filled out the form. So the bus will come, I think after 1:30, the bus will come here at the gate. And So we will leave promptly at 2, so don't be late. Inshallah, we'll try to leave promptly at 2. Okay? And we'll go to the Safe City Authority to see what they're up for.
So the seam carving is okay.
Seam carving.
Sir, I mean, आपने जो कहा कि 2 images हैं stitch करने से पहले seam carving along the seam उन्हें stitch करेंगे.
Yeah.
Sir, vertical line के along the stitch करना आसान है वो basically.
हाँ.
Sir, along the seam किस तरह करेंगे stitch?
Seam compute कर लिया आपने?
Seam वो तो simple algorithm है.
हाँ. तो seam compute कर ले तो आपने दोनों को same size का बना दिया ना पहले. उन्हें 0 padding कर दी ताकि वो दोनों अगर मैं ऐड करता हूँ एक दूसरे के ऊपर आने से. ठीक है. अब आप वो ओवरलैप एरिया में सीम कंप्यूट करें अकॉर्डिंग टू वंस आपने कर दी इमेज 1 को उतना ही रहने दें, उसकी ये साइड सारी 0 कर दें आफ्टर द सीम वाली साइड 0 कर दें, फिर इमेज 2 को इतना ही रहने दें, उसकी इधर वाली साइड सारी 0 कर दें, आप दोनों को ऐड कर दें बस.
इनसे जो
काफ़ी अच्छा स्टिच बनना चाहिए.
दूसरा बोनस पार्ट है सर, उसमें जो 5 इमेजेस करने हैं सर, वो हम सिर्फ डेमोन्स्ट्रेट कर सकते हैं मैनुअली हमने होमोग्राफी.
हमारा लेक्चर लूज हो गया.
क्या है वो?
आई थिंक ये वाला लेक्चर रिकॉर्ड नहीं हुआ जो सेकंड के बाद का पार्ट था. किधर गया सबलाइम टेक्स्ट कहाँ से खुल गया? VLC मीडिया क्विक टाइम न्यू स्क्रीन रिकॉर्डिंग. तो स्क्रीन रिकॉर्डिंग इसका मतलब चल रही है कहीं. क्या चक्कर है? ओह विल स्लीप. एक मिनट, सॉरी मैं आपको वो कर रहा हूँ बट आई नीड टू. मेरी स्क्रीन रिकॉर्डिंग अभी भी ऑफ. ओह इसका मतलब स्क्रीन रिकॉर्डिंग चल रही है. आई नीड टू स्टॉप.